Hi everyone, my name is Andrea Borghesi and I'm one of the authors of this paper. And today we are going to discuss regularized approaches for constrained machine learning. Okay, in the last few years there has been a lot of interest in ethical and trustworthy AI. But as we know, machine learning models can suffer from many types of biases. Possible solution has been found is to enforce desired properties over the machine learning model themselves, for example, to enforce fairness. In the past, regularization-based approaches for injecting constraints in a machine learning model have been introduced to improve their accuracy thanks to the expert knowledge. But these models can also be applied to the trustworthy AI case. In particular, regularization approaches tend to solve this problem. They want to minimize a loss function over a set of a vector of weight W, and where W is our parameter vector. L is the loss function. F is the model to be trained over the X input and the W parameter vector. Then another term is added to the loss, where C is the so-called regularization function, as it denotes a vector of non-negative constraint violation indices for M constraints. Critically, lambda is the vector of weights, also called multipliers. For example, these are two cases applied to the trustworthy AI. The typical approach to solve this kind of regularized problem is to adjust the lambda factor until a suitable compromise between accuracy and constraint satisfaction is reached. But we have to consider that in this case, we have two possibly conflicting sub-goals, the loss function and the constraint satisfaction problem. And these two sub-goals can also not point toward the same direction. So we have to consider this issue. And in this work, we want to provide, for the first time, a systematic overview of strengths and potential weaknesses of this approach. But let's start by reformulating the regularization approach that we've seen so far. We first have to embed the machine learning structure in the L and C function, as you can see here in the PR lambda formulation. And this allows us to treat in a uniform way convex and non-convex models. Then we are interested in the second formulation, PC theta, that allow us to understand the relationship between the unconstrained PR formulation and the constrained training problem. In this case, theta is a vector of threshold for the constraint violation indices. And in most AI applications, this is going to be the most natural formulation. The question that we ask ourselves is that can PC be solved indirectly by adjusting the lambda vector and solving the unconstrained formulation? The answer is yes, in a sense, and we're going to see it, and then we are going to detail that in the rest of the presentation. We first start by presenting the algorithm to solve this problem. This algorithm is simple. It explores the possible multipliers way, and it tries start by optimizing the unconstrained problem in order to find the optimal W star solution. This is some kind of search over the multiplier space. Then, if this W star solution does satisfy also the PC formulation, this W star solution is stored. And then in the end, we select the solution with the smallest loss associated. This should be theoretically equivalent to solving PC directly if solving the unconstrained problem has a chance to its assignments optimal also for PC, and if an optimum for PC theta is always attainable with this method. And now we are going to understand if it is always the case. Well, an optimal PC solution W star C satisfies this condition. Well, an optimal solution PR star with the multipliers lambda satisfies this condition. These definitions apply to both local optima and global optima. The first result of the paper is the theorem number one. An optimal solution W star for the regularized formulation and not constrained one is also optimal for the constrained formulation for a threshold equal to C W star. This has been proved in the paper, and I'm going to skip the detail here of the presentation. There is a proof by contradiction in the paper. And the key takeaway is that solving the unconstrained problem always results in an optimum for the constraint formulation, albeit for a threshold that cannot be a priori decided. This is true for non-convex loss, regularization terms, and model structure. This is a good result. This is a good starting result because it's promising and it tells us that we can, in theory, find some optimum for PC also by searching the optimum for PR. But this is not free of issues. For example, if PR has multiple equivalent optima, such as in this first case, in the fully convex case, the multiplier values may cause the presence of plateaus, as in the picture on the right. In the non-convex case, the problem is even worse. In this case, there might be separate optima with the same value for the regularized loss, but different trade-offs between loss and constraint violations, as you can see here in the purple highlighting on the right. In this case, multiple equivalent optima may cause a non-monotonic relation between lambda and the constraint satisfaction level. It may also happen that different constraint optima are associated to the same multiplier and no other multiplier. In this case, it could be impossible to reach the specific constraint optima unless we apply some kind of tie-breaking technique. Then there is an even larger issue that can be found by considering this question. Can we find an optimum for the constraint formulation? Can an optimum for the constraint formulation not be associated to any multiplier value? So do exist an accessible constraint optima? Well, theorem number 2 actually deals with the problem. I'm going to skip the detail here that you can find the demonstration and more thorough description of this theorem in the paper. But the key takeaway is that every assignment for which a certain constraint J has a lower degree of violation than in W star, it enforces an upper bound on the multiplier J. Instead, every assignment for which the violation is higher enforces a lower bound on the multiplier lambda. The main consequence of this theorem is that the system may actually admit no solution. And for this reason, there could exist some constraint optima that cannot be obtainable via the proposed algorithm. For example, in this case, for the optimum W star, threshold theta star, any multiplier value will result in an unbound regularization problem. This is a very serious limitation, as you can imagine, whose actual severity will depend on the specific properties of the loss, regularizer, and the machine learning model in question. Furthermore, there are additional issues with this formulation and with this problem with this regularized approach. First, we can have numerical issue. In some situation, reaching a specific optimum for the constraint problem might require extremely high or low multipliers, which can, of course, cause numerical issues at training time. Furthermore, there can be a problem between global and local optimality. Global optima are obtainable only in specific cases, convex problem, or by solving the regularized formulation exactly, which in turns can be computationally expensive. So in several situations, a most computationally viable approach would be to find only local optima. Finally, there is also the differentiability question, as many regularization-based approaches require CW to be differentiable. Just to recap, in this work, consider the integration of learning and optimization. And in particular, we saw how adding a regularization term to the loss of the learning can constrain this behavior. At the same time, we realized that finding the right balance between the learner loss and the regularization term and satisfying the desired constraint is not a trivial task. In particular, one of the key results of this paper is the demonstration that this type of approach, the approach to find regularized solution and then apply them to the constraint formulation, does not guarantee to find all optimal solution. This happens especially in the case of non-convex problem, where there might be optimal solution for the constraint problem that cannot be found by a corresponding exploration of the multiplier value space. And with this, I conclude. If you have any follow-up question, feel free to ask me now or to contact me at this email. Thank you very much for your attention.